In this lecture, we will work out an exercise on using the epsilon-delta definition of limit to prove a limit equation involving complex numbers. Let f of z be equal to u of xy plus I times v of xy. U of xy equals x cubed minus y cubed all over the quantity x squared plus y squared, and v of xy equals x cubed plus y cubed all over the quantity x squared plus y squared. Z equals x plus I times y. We will prove by using the epsilon-delta definition of limit that the limit of f of z is 0 as z approaches 0. Let us recall the formal definition of limit. The limit of f of z as z approaches a is L if and only if for every epsilon greater than 0 there exists delta greater than 0 such that the absolute value of f of z minus L is less than epsilon, whenever 0 is less than the absolute value of z minus a is less than delta. For this exercise, the limit L is 0, and the value of a to which z is tending is also 0. With epsilon-delta proofs, we often work with what seems like the reverse direction. We start with the epsilon inequality with the absolute value of f of z. If we set the absolute value of f of z, or the absolute value of u of xy plus I times v of xy, if we set this less than epsilon, then we find delta. The triangle inequality still applies to complex numbers, so that the absolute value of u plus I times v is less than or equal to the absolute value of u plus the absolute value of I times v. The absolute value of I is 1, so that the absolute value of u plus I times v is less than or equal to the absolute value of u plus the absolute value of v. We replace u and v by their respective definitions, and find that f is less than or equal to this time, this sum of absolute values. We will use polar coordinates for the rest of the proof. We set z equal to r times e raised to the power I times theta, where r equals the absolute value of z and theta is an argument of z. Since r equals the absolute value of z, r less than delta is the inequality we are aiming for. X equals r times cosine theta and y equals r times sine theta. So replacing x by r times cosine theta and y by r times sine theta, we get u of xy equals r cubed times cosine cubed theta minus r cubed times sine cubed theta all over the quantity r squared times cosine squared theta plus r squared times sine squared theta. Since z is only approaching 0 and so is not yet equal to 0, its absolute value r should be greater than 0 so that we can cancel out r squared. Cosine squared plus sine squared equals 1, so that u simplifies into this quantity. After the application of the triangle inequality, the absolute value of u should be less than or equal to the absolute value of r times the sum of the absolute values of cosine cubed theta and sine cubed theta. The absolute values of cosine cubed theta and sine cubed theta are both no greater than 1. Therefore, the absolute value of u is less than or equal to r times 1 plus 1, or 2r. Similarly, v simplifies into this expression, and that the absolute value of v is also less than or equal to 2r. So we now have this sequence of inequalities. The absolute value of f of z equals the absolute value of u plus I times v is less than or equal to the absolute value of u plus the absolute value of I times v is less than or equal to 2r plus 2r, or 4r, so that the absolute value of f of z is less than or equal to 4r. If 4r is less than epsilon, then so will the absolute value of f of z by transitivity. So we set 4r less than epsilon so that r is less than epsilon over 4. This inequality has the form that matches the delta inequality that we are aiming for, where we have r less than something positive, and surely epsilon over 4 is positive, since epsilon is positive. So we choose delta to be equal to epsilon over 4. Now that we have found delta, there's a second part to the proof that we must not overlook, and that is we must show that the epsilon inequality holds for the delta value that we have just found. That is, if delta equals epsilon over 4, we must show that the absolute value of f of z is less than epsilon. This time, we start with the delta inequality. If the absolute value of z or r is less than delta, and delta is epsilon over 4, then epsilon is greater than 4r, or 2r plus 2r. 2r is greater than or equal to both the absolute value of u and the absolute value of v. This is a fact that we found simply by using polar coordinates and is therefore independent of epsilon and delta. Therefore, 4r is greater than or equal to the absolute value of u plus the absolute value of I times v. Recall that the absolute value of I is 1. Because of the triangle inequality, this last sum is greater than or equal to the absolute value of the sum of u and I times v. U plus I times v, of course, is f of z. So by transitivity, the absolute value of f of z is less than epsilon whenever 0 is less than the absolute value of z, and the absolute value of z is less than epsilon over 4, or delta. Therefore, the limit of f of z is 0 as z tends to 0.